Imagine floating alone in space. Just you, your spacecraft, and the endless stars stretching in every direction. Peaceful, quiet, almost like time itself has stopped. But then, something strange appears ahead. A dark, swirling shadow. A black hole. Its gravity is so strong that nothing, not even light, can escape it. Our astronaut drifts closer, curiosity pulling him forward. And then, he gets too close. The black hole's gravity takes over. The spacecraft shakes, time stretches, and everything around him starts to warp. At first, it is pure darkness. But slowly, strange visions begin to appear. Memories from his own past, childhood moments. Old friends, forgotten dreams, flash before his eyes, as if the black hole itself is showing him his life. This strange idea has even been shown in the movie Interstellar, where the character falls into a black hole and experiences time in a completely different way. But could this really happen in real life? Today, we're going to explore everything about black holes, from how they are formed, to the incredible forces they hold, to the mysteries of time and space near their edges. So get ready, because we are about to dive deep into one of the most fascinating and mind-bending objects in the universe. After understanding what a black hole feels like, let's now answer the most important question. How are black holes actually formed? Black holes are not born randomly. Scientists believe they form mainly in two different ways. The first and most common way begins with stars. Stars are not eternal. They survive by burning fuel in their core, mainly hydrogen. This fuel creates energy that pushes outward and balances the star's own gravity pulling inward. As long as this balance exists, the star remains stable. But when a very massive star, around 8 to 10 times heavier than our Sun, runs out of fuel, that balance breaks. The outward pressure disappears, and gravity suddenly wins. The star collapses violently under its own weight and explodes in a massive supernova. What remains after this explosion is an incredibly small and dense core. If the original star was massive enough, this core collapses completely, forming a black hole. However, not all stars become black holes. Stars with lower mass do not collapse enough. Instead, they leave behind other dense objects, like neutron stars or white dwarfs. Only the most massive stars have the power to create black holes. But this is not the only way black holes are formed. There is another, more mysterious pathway. In this second process, black holes form directly from massive clouds of gas. Instead of first becoming stars, huge amounts of gas collapse all at once under gravity. There is no supernova, no long star life, just direct collapse. This process creates much larger black holes, with masses ranging from thousands to even hundreds of thousands of times the mass of our Sun. Scientists believe this type of formation happened mostly in the early universe, when huge clouds of gas were common. These massive black holes may have acted as seeds, slowly growing over billions of years into the supermassive black holes we see today at the centers of galaxies. So whether born from dying stars or from collapsing gas clouds, black holes are extreme products of gravity, formed when matter is squeezed beyond all limits. For a long time, black holes were not something astronomers could see. In fact, they were first discovered not with telescopes, but with mathematics. In 1915, Albert Einstein published his theory of general relativity. This theory explains something completely new, that gravity is not just a force, but a bending of space and time itself. According to Einstein, massive objects like stars and planets change the shape of space around them, and this curved space tells objects how to move. Soon after, a German scientist named Karl Schwarzschild found a special solution to Einstein's equations. His calculations showed that if enough mass is squeezed into a very small region, space and time would curve infinitely, creating a point from which nothing could escape. This was the first mathematical description of a black hole. According to this solution, space would be distorted so extremely that it would be like a hole or a tear in the fabric of spacetime. However, at that time, scientists were not sure if such strange objects could actually exist in the real universe. Even Einstein himself was doubtful. For many years, black holes were seen as mathematical curiosities, interesting on paper, but possibly unreal. Things began to change as astronomers started discovering the remains of dead stars. One such discovery was neutron stars, detected as pulsars, tiny, incredibly dense objects spinning rapidly and sending out regular radio signals. If nature could create something as extreme as a neutron star, scientists began to realize that black holes were not impossible after all. They were likely the next step for even more massive stars. The real breakthrough came in the 1960s, when astronomers detected a powerful X-ray source called Cygnus X1. This object was invisible, but it was pulling matter from a nearby star. As this matter fell in, it heated up and released intense X-rays. The invisible object was too massive and too compact to be a neutron star. It was the first strong evidence of a real black hole. From that moment on, black holes moved from theory to reality. What was once just a solution to equations became one of the most important and fascinating objects ever discovered in the universe. When we hear the words black hole, many people imagine a giant dark vacuum sucking everything in. But in reality, black holes are more complex and more fascinating than that. A black hole can be thought of as having three main parts, or layers. The first and most important layer is called the event horizon. This is the invisible boundary around a black hole. Once anything crosses this boundary, light, matter, or even time itself, it can never come back out. The event horizon is often described as the point of no return. From the outside, gravity near this boundary feels incredibly strong, but interestingly, gravity itself does not suddenly spike at the event horizon. What makes it special is that escape becomes impossible beyond this point. Inside the event horizon lies the most mysterious part of a black hole. At the very center is something called the singularity. This is where all the mass of the black hole is crushed into an unimaginably tiny point. At the singularity, our current laws of physics break down. Space and time become infinitely curved, and scientists still don't fully understand what truly happens there. Because black holes do not emit light, we cannot see them directly like stars or planets. Instead, astronomers look for their effects on nearby matter. When gas and dust fall toward a black hole, they don't fall straight in. They begin to swirl around it, forming a bright, spinning disk called an accretion disk. As this material heats up, it glows intensely and releases radiation, especially X-rays. This glowing material allows scientists to detect the presence of a black hole. However, supermassive black holes often sit in the dusty centers of galaxies. Thick clouds of gas and dust can block much of this radiation, making them difficult to observe. A historic breakthrough came in 2019 when scientists released the first ever image of a black hole located in the galaxy M87. This image was captured by the Event Horizon Telescope, a global network of radio telescopes working together as one giant, Earth-sized telescope. The effort was enormous. Even after the data was collected, it took nearly 2 years to process, because the amount of information was too large to send over the internet. What we see in that image is not the black hole itself, but the glowing ring of hot matter around the event horizon, with a dark shadow at the center. Scientists now hope to capture more images of black holes in the future. One major target is Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A is especially interesting because it is quieter than expected. Studies suggest that strong magnetic fields may be limiting how much material falls into it. Other research has revealed a cool gas cloud surrounding it, giving scientists a clearer picture of what the environment around a black hole looks like. Slowly, image by image, we are beginning to see the invisible and understand what these cosmic giants truly look like. So far, astronomers have identified three main types of black holes. They differ not in what they are, but in how massive they are and how they are formed. Let's start with the smallest and most common type. Stellar black holes are formed when massive stars die. When a large star burns through all of its fuel, it can no longer support itself against gravity. The star collapses inward, and if it is massive enough, this collapse creates a stellar black hole. These black holes are relatively small compared to others, but they are still extremely powerful. Their mass is usually a few times the mass of our Sun, yet all of that mass is squeezed into an incredibly tiny space. Even though they are called small, their gravity is strong enough to trap light and destroy anything that gets too close. Stellar black holes are scattered throughout the universe, formed wherever massive stars once lived and died. Now let's move to the giants. Supermassive black holes are the largest black holes known. They are millions or even billions of times more massive than the Sun. What makes them even more surprising is that, despite their huge mass, they are not much larger in size than stellar black holes. Scientists believe that almost every galaxy has a supermassive black hole at its center, including our own Milky Way galaxy. These black holes dominate their surroundings, controlling the motion of stars, gas, and entire galaxies around them. How they formed is still one of the biggest mysteries in astronomy. Many scientists think they grew from smaller black holes in the early universe, slowly gaining mass over billions of years. Between these two extremes lies the most mysterious category. Intermediate mass black holes sit between stellar and supermassive black holes. For a long time, scientists were not sure if these black holes even existed. One possible way they form is inside dense star clusters. When many stars are packed closely together, they can collide and merge in a chain reaction. Over time, this process can create a black hole much larger than a stellar one, but not large enough to be supermassive. Several of these intermediate black holes may later come together and merge, eventually forming a supermassive black hole at the center of a galaxy. In recent years, evidence for intermediate black holes has grown stronger. In 2014, astronomers found signs of one in the arm of a spiral galaxy. Then in 2021, scientists used data from an ancient gamma-ray burst to detect another possible intermediate mass black hole. These discoveries suggest that black holes come in many sizes, and that each type plays an important role in shaping the universe we see today. Black holes are not just strange, they completely challenge our understanding of reality. And some of the facts about them are more terrifying than fiction. Let's start with one of the most famous stories, falling into a black hole. If you were to fall into a black hole, scientists believe you would be stretched apart like spaghetti. This effect is actually called spaghettification. It happens because gravity near a black hole is much stronger at your feet than at your head, pulling your body apart lengthwise. According to older theories, this stretching would continue as you fall in, and you would die long before ever reaching the singularity at the center. But things get even stranger. In 2012, a study published in the journal Nature suggested something far more extreme. According to this idea, powerful quantum effects near the event horizon could turn it into a kind of wall of fire. Instead of slowly being stretched, anything falling in would be instantly burned and destroyed the moment it reached the event horizon. This idea is still debated, but it shows just how mysterious black holes truly are, and how little we still understand about the laws of physics under such extreme conditions. Now let's clear up one of the biggest myths about black holes. Black holes do not suck everything in like cosmic vacuum cleaners. Suction happens when something pulls matter into an empty space, but a black hole is not a vacuum. It is simply an object with an enormous amount of gravity. Objects fall into black holes the same way objects fall toward Earth, because of gravity. If our sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting almost exactly the same way as before. You only get pulled into a black hole if you come very close to it. So, black holes are not hungry monsters roaming the universe. They sit quietly in space, obeying the same gravitational rules as other objects, just on a much more extreme level. Here's a fact that might completely change how you see our own galaxy. Astronomers estimate that the Milky Way alone contains anywhere between 10 million to 1 billion stellar black holes. These are black holes formed from dying stars, each with a mass roughly 3 times that of our Sun. That number might sound shocking, and it is. Most of these black holes are completely invisible. They are not actively pulling in gas, they are not glowing, and they are not announcing their presence in any way. They simply drift silently through the galaxy. This means that our Milky Way is likely filled with millions of hidden black holes, quietly orbiting the galaxy just like stars do. Some may be relatively close to us on cosmic scales, yet impossible to detect unless they interact with nearby matter. So, when we look up at the night sky, what we see is only part of the story. Beneath the visible stars lies a dark population of black holes, silent reminders of massive stars that lived, died, and collapsed long before humans ever existed. Black holes began as equations on paper, pure mathematics predicting something so extreme that even Einstein himself doubted it was real. Today, we know they exist. We've photographed them. We've detected their collisions through ripples in spacetime itself. And yet, we still don't truly understand them. Some physicists believe black holes may destroy information forever. Others believe that information is somehow preserved, encoded on the event horizon, or released slowly over unimaginable timescales. And then there's an even stranger idea. What if black holes are not just cosmic graveyards, but cosmic gateways? What if, hidden behind the event horizon, lies another universe, or the beginning of a new one? We don't know. Right now, somewhere in the universe, matter is falling past an event horizon, crossing a boundary we can never observe beyond. And whatever happens next, the universe keeps it secret,